Hello, everyone. Welcome to my talk on AI and financial econometrics. Let me start by introducing myself. I am Ambika Sukla. I lead Morgan Stanley's AI and Machine Learning Center of Excellence. So today's talk is, there's a lot of chatter in the press about how AI is going to change finance. What I'm going to do today is I'm going to walk you through some specific examples of how AI can help finance, especially how AI can help financial econometric modeling process. And I'll do that by using three concrete examples. And you may not have seen these examples before. These are a few things that I have put together over the last few months. Before I start, what is financial econometrics? Well, simply put, it's the science of understanding financial instruments, financial markets. And typically, a lot of math and statistics is involved as you try to understand econometrics. And today, my focus is going to be on three things. One is a very basic problem of finance, which is forecasting and trend detection. And the second is volatility modeling. And the third is optimal trading strategies. Now, most of this is not all that econometrics can do. In fact, financial econometrics is leveraged in almost every area of financial modeling. And there are so many other interesting problems. But the ideas that you are going to get today, you can easily go ahead and apply them to all those interesting problems like arbitrage, market making, risk management, portfolio optimization, and so on. Let me start by giving you a couple of introductory slides, and after that the real fun will begin. The first slide is, let's look at what is involved in a traditional econometric model. What is it? Well, as Professor Germani was talking about in the morning, in a traditional model you'd have simple models, mostly linear models. And there are many assumptions made and handcrafted features and known probability distributions like a normal distribution or a Bernoulli distribution would be used. And why would you do that? Because you need to keep the model simple so that you can understand it and also do mathematical analysis on the model so that you can do model inference. And these are the most widely used inference methods, maximum likelihood and Bayesian inference. In both the cases, for every model, you have to do tons of mathematical derivations. And if you want to know what I'm talking about, again, look at Professor Germani's paper on Kalman filters and EM analysis. It needs a lot of math. And model testing is nothing revolutionary there. So to put it simply, when we are talking about econometric model, we're talking about data plus simple models plus lots of math, lots of complex math. Now, how does an AI model, what do I mean by AI? What I mean by AI here is that I'm talking about models that are almost like black box. So I'm talking about a neural network type of model where you only specify what your objective is. You set the problem up and you specify your objective. And you can relax some of the assumptions that we typically use in traditional modeling. And the methods here, the inference methods here are gradient descents and their variations. And there are black box variational inference. There are few generative models type of approaches there. And again, model testing is not very different. So in short, when we're talking about AI econometric model, there's lots of data plus complex models, plus we are using a optimizer. So this is all good. Let's look at some specific examples. I'm going to start with something called trend detection. And this is a very fundamental problem of finance. It's also referred to as smoothing. What I mean by this is, let's look at an example. What I have here is a simulated stock price. So on the x-axis, I have time. Y-axis, I have simulated stock price. And you can see that there is an upward trend from point P1 to P2. And there is a downward trend from P2 to P3. How do you find this out mathematically? What we can do here is we can draw a line, and that's called the regression line. That's a very most basic thing in finance, a regression line. So you take all the points between P1 and P2, and you run linear regression on them. You draw another line, that's the downward trend right there. But the problem here is that it's very hard to figure out what those P1s and P2s are. You have to keep trying different windows to understand which P1s and P2 you're going to select. So there is another method which is much more sophisticated, and this is called Kalman filter. I'm going to very quickly go through this because it's not the main topic of discussion really. The way Kalman filter works is, let's say there's an object in two-dimensional space. So it could be a bird flying, it could be a vehicle on the road, or it could be a stock price that you are watching. So that is the true position of the object. But when we take a measurement, what you get is that, the green circle. So now our job is to estimate where the object really is. So let's say I start with this as my guess. Okay? And in the next time step, the object moves to a new location. Now I have to figure out where is this object. So I'll take a guess, and let's say it's over here. And this is just my belief. I'm not very confident about where this object is. And what I'm going to do is, when I get the measurement, I can update my location to the new spot here. So as I get my measurement, I'm much more confident, and so on and so forth. I can keep doing this, and as you can see, that even when my measurements are far off from reality, I am still being very accurate about where I am. So this was developed by Rudolf Kalman way back in 1960, and it has been used for everything starting from self-driving cars to tracking satellites to doing financial econometrics. In fact, Stanford, the Stanley, the car that won the first prize in 2005, they used Kalman filters extensively. So let me see which AI model. In this particular case, I selected ConNet to be my AI model, and I know a lot of you are probably familiar with what this is, but I'm just going to walk you through it for the benefit of those who haven't seen this before. Let's say I'm looking at a picture, and the picture is that of delicious Indian food, and my job is to figure out what is there in the picture. So what I will do is I will scan this little filter from left to right and top to bottom. And I will not just have one filter, but I'll have many such filters that does this work for me. And it has been shown that as you train this network to identify pictures or do object recognition, the filters start taking some meaning. So you'll have one filter which is like a horizontal line, another filter which is a diagonal line, another filter which is a vertical line. And it's not just about lines. You can have a filter that is looking for green color, another filter, a red cross maybe, and maybe a mixture of green and red. So that, in a sense, is ConNet. Now, this ConNet is sort of a substitute for all the handcrafted filters that were used for image recognition in the past. So let's see how we can apply this in finance. Well, it turns out that finance had these handcrafted filters for a long time. And you can look at a time series as something of a one-dimensional picture, and you can move a ConNet just the way we did for the picture over here. And it looks, and there are some well-known filters. Identity filter just gives you back where what it sees. There is this well-known, this is the most popular, most important tool in finance, which is moving average. And that is nothing but a filter as well. It's just an average of the last 5 objects, last 5 prices. And then we have exponential weighted moving average, which is simply, it gives more weightage to recent numbers. And then the famous autoregression, the AR filter, you can think of that as something that has weights derived from the data, right? So with the background material all set, let me talk about my model. So this is what I do here. I start by simulating a set of trends. And you see there are slopes which are going up and going down, and slopes that are staying flat. So I create many such examples of simulated trends, and to that I add Gaussian noise. So what I get back with that is a noisy version of those trends, and the blue line is what it is. And to that, I am now going to pass it through a model. So my model here is nothing but a set of 64 Kohn filters, which are one-dimensional, and with some activation. And just a little tip here: if you're looking at financial data, tan-H activation works better than sigmoid or ReLU. And then this is my objective. This is the goal that I gave to my network. That hey, when you see this noisy version of my signal, give me back my signal. So it's almost like a denoising filter, and this has been around for a while now. People have done work in this in the 90s as well. And let's look at the results. It's pretty remarkable. As it gets a simulated series which has similar noise, it's doing great. It is the red line is what is the output of my model, and it's able to very nicely track the mean. No problems at all. And let's look at it a little bit closely. Even when the variance is very high and there are these spikes, it's still able to do a really good job at staying with the mean. And here's a comparison with AI with a Kalman filter. If you notice there in the Kalman filter, which is in black, it doesn't respond to the spike very well. It kind of tries to follow the spike, whereas the ConNet filter, the AI filter, is very robust to that as well. Now you may say that, oh, all this is very good. What about real data? Yes, you generated some fake data, and of course it worked. So let's try it on some real data, right? Here's I'm trying this on S&P 500. I took 200 days of S&P 500 and was beautifully able to draw a line all the way through the mean with smoothing. And if you compare with the black line, it's almost as good as, or maybe sometimes better than, Kalman filter in the task of smoothing, which is phenomenal, because if you think about it, what we just did is we replaced something that has been there for decades, and we're able to come up with something without. I mean, there is a lot of math in ConNets, but we are not exposed to that math. But we are just, by using a black box model, we are able to create a smoother. So what is the purpose of a smoother? Well, you can use the smoother for price forecast. You can use the smoother just to find out trends. And it so happens that in finance, and like the previous speaker said, in finance, it's not a worthwhile objective to try to forecast prices, because it is a random walk, and it's just too hard to forecast prices. What people are interested in is volatility, which is the topic of my next example. So here I'm going to use something called generative adversarial networks to do volatility modeling. And this is something quite new, and we are working on a paper around this topic. So what's volatility? Well, volatility is nothing but it's just the standard deviation of returns. So in the top, you are looking at the red. On the top slide there is returns, and the bottom is just the volatility of the returns. And you can see that when the volatility is high, there is more fluctuations in the return. When volatility is low, there is less fluctuation in the return. Now, why do we need this model? Well, it's needed for the Black-Scholes formula for derivative options pricing, and that's one of the most famous formulas in finance, and it expects you to feed in the volatility. And it's also used for other stuff like market making, for portfolio management, risk management, and so on. let's take a look at what is a volatility model. Let me just explain what is it that we are trying to model really. Well, what we have are observable components. We are able to look at the returns, but we don't know what is the underlying volatility. We can only look at the returns. The return at time t is RT, and the return at time t minus 1 is RT minus 1. What we want to find out is the volatility that is generating that return, which is sigma t at time t, sigma t minus 1 at time t minus 1. And it has been shown that they are related. Volatility exhibits clustering, meaning periods of high volatility is followed by periods of high volatility. And in certain models, there is a stochastic component as well, which is added to this, and those are called stochastic volatility model. And you pick any book in financial econometrics, you'll have pages after pages dedicated to volatility modeling. It's so important that some of the folks who developed volatility models in the past, they have Rob Engel, he developed the first one, which is called ARCH, and he received a Nobel Prize in 2003. So what's our goal? What are we trying to do? Well, our goal is to look at those returns and tell what the volatility is. Before we do that, let me explain the model that I'm going to use. It's called generative adversarial network. And I'm pretty sure a lot of you are familiar with it, but again, for the benefit of everyone, I want to go through it. What's going on here? Well, this is a very remarkable thing that came up in the last 2 or 3 years. Someone named Ian Goodfellow, he came up with this. It's very, very remarkable in some of the things it can do. So let's say in GAN, there's a generator that takes random noise, and it generates some signal, okay? And then there's a discriminator which kind of looks at that signal, and we also alternatively feed in the real signal. So there is the generated signal is considered the fake signal, and the real signal is the data of which the data for which you are doing the probability distribution. So as we are able to feed this data alternatively, the discriminator forces the generator to be able to generate data that looks very real. So for example, if the real data is pictures of lots of pictures of dogs, right? At the end of this training, if you go to the generator and say that give me some data, it's going to give you a totally artificially generated picture of dog. And that's what is so remarkable about this technology. In other words, it has understood the probability distribution of what a dog looks like. So how can we do volatility modeling with this? Can we maybe take this returns and just feed the returns? Maybe that's going to give us the volatility. Well, no, that doesn't work because we are looking for is volatility. I mean, this is going to give you the returns. It's going to give you numbers between -1 and 1, but it's not going to give you the volatility. What if we just feed in volatility directly? How about that? We just take the VIX numbers and then it can generate volatility. Great, but that's not going to work either because the volatility should be dependent on the returns in some way. You can't just arbitrarily generate it. I mean, it's going to generate some number between maybe 10 to 80, but that's not going to be reflective of the time period at which you are looking at this. So to solve this problem, what we are doing is we're looking at something called conditional GAN. So we are giving a condition to both the generator and the discriminator as we train. So to go back to the dog example, let's say I give a condition which is a type of the dog. Let's say as I am feeding in pictures of lab retriever, I say that this is a lab retriever. So at the end of this, I can then ask it to generate pictures of lab retrievers. So now it is the generator has not only learned how to generate pictures of dogs, but it can also generate under a certain condition. If you give a name, it's going to give you the type of the pictures of that type of dog. So how do we do volatility modeling with this idea? What I did here is I fed in lagged returns. So I fed in and I want to explain what lagged returns are. At any point of time when you're looking at the returns, if you take the last 5 points, those are lagged returns. So I fed in that to both the generator and the discriminator. And then here's the trick that finally made this work, which is, yes, if I do this, then the linear layer in the generator, the only thing it's going to generate is again signals. It's not going to give you the volatility. So I take whatever it is generating and I multiply that. I multiply that with a random number sampled from a normal distribution. And as I do that, and the signal here is this. As I do that, let's see what happens when I do that. This slide is explaining it a little bit further. Let me explain how I trained it. So first I generated volatility, which is a randomly generated process. I'm doing synthetic data here again. And what you see below are the returns for the corresponding volatility. And what I'm feeding to this network are those little the rectangles, which is the lagged returns. And what I just want to make sure that I'm absolutely clear about it is what the network doesn't see is the volatility. It never got a chance to see that. It only saw the returns. And that's the purpose of a volatility model anyway. So here are the results. And what you see here is in the first slide, you're looking at the actual volatility that I used to generate the returns. So this is the volatility that, again, it's a good idea to start with something very simple and then move on to complex. So what I did here is I kept only 4 or 5 different volatility numbers, and I generated those observed signals out of it. And as I did that, the generator is now able to generate the signal that represents volatility of the underlying series. So in other words, if you want to do something like regime detection, you can feed in the signal into this generator, and it's going to tell you the regime totally automatically. And let's see if this idea works for other types of signals or not. Well, in this particular case, the volatility signal is going up, and I mean it's taking a sort of a shape here as opposed to just being a square wave sort of thing. And here again, as you can see, which is this one here is the actual volatility that I used to generate the data. This one here is a return, and this one here is samples from the trained GAN, and this one here is the mean of the volatility. So as you can see, it's able to just take this signal and reconstruct the variance of the signal simply by looking at the signal. And what I'm again, it's very important to understand that we are feeding this. We are never showing our GAN the actual volatility. So purely by looking at this, it's able to generate the volatility. You have a question? Could we give it towards the end? I have another example I need to go through. So you might ask, where is real data? Well, that is coming. So we'll have a more elaborate, I guess, paper describing this method, and we'll test on real data. We'll test on S&P 500, compare that to VIX and other models, and so on. Now, the next example that this is all good, but I know we are here because we want to learn how to make money, right? So let's see how we can make money. And the next example I'm going to show is that of a technical trader. Okay, and I'm going to show you how to use reinforcement learning to come up with some trading decisions. All right. So here, what is a technical trader? There are 2 types of traders. One is technical, that only looks at the chart and makes all their decisions based on patterns they see in the chart of a underlying stock or bond or whatever it is, right? They are not concerned, like fundamental traders would be concerned about, is there a CEO change? Was there a product announcement? Was there some kind of merger? They don't care about any of that. They just look at signals in the charts. And here's the one method for technical signal analysis. It's the most basic method, which is you take the price and then you do the moving average of the price. Whenever the price crosses your moving average point, it's a buy signal. Whenever your price falls below the historical moving average, so this is a sell signal right here, and this is a buy signal. This is a buy signal. And believe it or not, if you look at a library like TALib, there are 150 such signals that you can arbitrarily combine and do all sorts of technical analysis that you can think of. So the model here that I have selected is reinforcement learning, and once again I am sure many of you know about reinforcement learning, but for the purpose of those who don't, I'm going to explain it. In reinforcement learning, we have a state, we have an environment, and we don't know what the environment does and what is inside the environment. We can ask it, hey, give me your state. So it will give me the state, but I just don't know how internally things work in the environment. Then we have a actor or a policy function that can take this state and take some action on the environment. And as it does that, you will get back, the environment may sometimes give you some rewards. If you do something good, you will get a reward. If you don't do something good, you will say nothing. It will just give you the next state. Right? And then there is a critic who is going to look at what you are doing. It's going to look at your actions, and it's going to take a look at your actions, the rewards it got, the state transitions, and it's going to tell you how good a job you did, and that's the feedback. And as it does this cycle over what is called episodes, the critic forces the actor to take the most optimal decisions given a certain state. And this is very effectively applied. If you look at the Google's AlphaGo, they use reinforcement learning, some self-driving cars. It's pretty widely used these days. So let's see how we can use this for our purpose. So in our case, the environment would be stock prices. So what we are looking at stock prices. Now you have no control over it. It's just moving, and that's what you're looking at. And the state can be lagged prices, okay, and current P&L. This is how much money you are making so far, and the current position. Your actions here could be the buy-sell decisions, and your reward. So in my model, what I said is, hey, look, if you do a buy or sell decision, and you're going to make, if you're making positive P&L, you're getting 1 point from me. That's if you don't make positive P&L, even if you are negative, I won't say anything bad. I will just give you 0. But if you make positive P&L, you get 1. So with that approach, let's see what happens. And what happens is actually pretty remarkable. So what you're looking at here is on the top, it's prices, and then the actions. And actions are buy and sell. This is the moving prices. And this is your P&L as time progresses. This is a simulated price. Okay, so it's a lot of what I'm showing today is simulated price. And one of the good things about simulated price is you have a lot of control over what you are doing, and it's easier to prove out some ideas using simulated data first, and then. I'm sorry. It is not Brownian motion. It's a Uhlenbeck process, which is again mean reverting, and that's the reason why it learned what it learned. So in real life, not everything is mean reverting, but this is a mean reverting process, which is a simulated. Exactly, and because it's a mean reverting process, it's able to make those decisions. Exactly, that's correct. So what's happening here is that if you look at this, the price, when the price drops, it's automatically able to figure out that it should start building position because the price is dropping. It's starting to do a lot of buys, and as the price goes up, and it does in 2 occasions, it's starting to sell. It's not selling everything right away. It is sold a little. It's looking at the slope also in some way, and sold a little in both instances. And both the times, it had a P&L bump right there. And this is the P&L bump that I'm talking about. Up P&L, up P&L. And it's so this learned the most basic thing in finance, which is buy low, sell high. So it just and this took 2 minutes. Everything I showed here, it took just a couple of minutes of training, because I had a lot of control over the data that I was trying to use. I didn't churn this thing for for 30 days or use like thousands of GPUs or any of that. On my laptop, it was just a couple of minutes of training. So let's look at another example, see if it was not a fluke, right? And I have many such samples. I picked a couple that looked very interesting. So here again, there is a big price dip here, and it goes ahead and builds up position as there is a price dip. And then same thing, as the price goes up, it tries to, it does this big sell here, and all of a sudden it goes up. It has a huge bump that it gets in the P&L. And this is all good. A few things can be changed in the model. One problem here is that it is left with position. Ideally, you don't want to have any risk. So you want to go in there with nothing. You want to come back with money and nothing else. But here it is left with some position. And this is just an idea. You can take it from here and kind of improvise and come up with new ideas around this. So what I showed today is a way to look at to transition from traditional AI models, from traditional models to AI models for financial econometrics. So how do you do it? You take a traditional model, you understand it, you read everything that has been done over the last 60, 70, 80 years. Do not ignore that, because that's what is going to give you ideas about what the input should be, what the output should be, what should be the objective function, and so on. And then look at the assumptions. Every model has assumptions, many, many assumptions. Look at the assumptions and see if you can relax those assumptions, right? Because that's the whole point. The point is to be able to automatically figure it out no matter what it is, instead of saying that, hey, I think this is a Gaussian, I'll start with that and see what happens, right? And then next is you select, well, I would say select model, not select neural network. Select the model and select objective function, train. In train, try to train as much as possible with synthetic data to begin with, because if you train on real data, you'll spend a lot of time iterating over the data without getting anything meaningful. So you start with the iron out all your bugs with fake data, and then try it on real data. And the next thing is you compare results with the traditional models, and that's important. Why are we doing this? What problem is this solving? Is it making things faster? Is it making things more accurate? So make sure we compare that with the models. And lastly, it's what I shown today is it's really not very hard to create fully automated AI models for financial modeling. However, just be careful that you understand the models that are in place thoroughly, that are in place today thoroughly. And be creative. Take some ideas from here, some ideas from there, mix it up, and see what you can come up with. Start with toy examples, and then one thing that's very important in finance is the models. The black box models are not very interpretable, so be mindful of that. It's still an active area of research. Nobody has really figured out mathematically how to evaluate or interpret these models. But that's a good area of research. And that concludes my talk. We are hiring. You can reach me on LinkedIn. I guess I can take a few questions now. Sure.
Both the last two models where you use the reinforcement learning, the volatility one, it looks like you have to train the data, right? Thank you. With some simulated, you have to train the data with simulated, prices that follow certain dynamics from a volatility, right? And then you estimate the volatility based on that assumption about your trained data, which you simulated. So what happens, I'm asking you, what happens when the volatility doesn't relate to price the same way as your trained data? You know what I'm saying?
Yeah, well, okay, so what I showed you is the first cut of the work. It is just to prove out something that I want to show that if you are using GAN in a certain way, you can actually reverse engineer the volatility, right?
So I'm just saying, like, you have in the last model, the reinforcement model.
Yeah.
It's fundamental, I think, that for the price that you are making money with,
Right.
follows the dynamics of the price with which you train reinforcement.
That is true.
You use the Austin-Beck process for simulating and training.
Right.
And suddenly the market is like a momentum market. So I mean that's what.
Absolutely. I mean, these are toy examples. I won't recommend just taking this idea and straight away running and trying to make money. I mean, a lot of work needs to be done to go from here to actually making money in the market. Yeah. Well, we have tried, but I don't have the results to publish today. But any other questions?
Yeah. When you're building like a convolutional neural network, how do you decide your kernel size when you're convolving on time? Like I think you did a 1/5 kernel.
Right.
Like, do you guys have like a certain set of rules that you abide by? So if it's a 30 time step problem, your kernel's 1/5 or 1.6? I was just curious.
Yeah, sure. Normally, it's never a 30 time step problem because the way this is technically done is by using ACFs and PACFs. So you take the time series, you do a ACF of that. That's going to tell you how many autoregression, how many points, how far back you should go to do autoregression by looking at the data. And typically, it comes out to 1, 2, maximum 3. It never comes out to even 5. So if you are trying to feed in 50 time steps, it's not going to work. Because it's rarely correlated with 50 time steps. So I chose something which was not too small. 2 would have been ideal, but would have been a little kind of boring to look at. So I kind of added 3, 4 more and made it like more like AR5, AR6 models. Any other questions?
Thanks so much for sharing. Just curious, how do you balance the trade-off between sharing great things like this with the broader financial community, but also thinking through a little bit more of like the traditional protectionist style of, figuring out stuff and kind of keeping that behind Morgan Stanley's exterior walls?
Well, what I showed you today are really experiments, and they are mostly done with fake data, and everything that I showed you, there is really not a lot of proprietary information in there. So what we try to do is, if there is something to share without giving away all the secrets, then we make an effort to be visible in the community and kind of share any new discoveries that might be there. I hope that answers your question.
Will the paper be available on archive?
Yes. Yeah.
Any other questions? Okay, let's thank the speaker.
All right. Thank you. Thanks.